Hi, good morning. I'm Eileen Fong, an assistant professor at the School of Material Science and Engineering at NTU. Today it is my pleasure to introduce to you Professor Carl Barry Sharpless, our keynote speaker for today. Professor Sharpless is the W.M. Keck Professor of Chemistry at the Scripps Research Institute in California. A prolific researcher in chemistry, Professor Sharpless is passionate about finding new useful methods for chemistry. His imagination and vision led him to discover a series of reactions for the selective oxidation of olefins. His achievements have won him the Nobel Prize in Chemistry in 2001. Since olefins are one of the cheapest functionalized organic starting materials, his discovery has profound and widespread impact on academic and industrial chemistry. Professor Sharpless' current research focuses on click chemistry, his new synthetic stratagem for rapid discovery of chemical function. May we now invite Professor Sharpless on stage to share with us on how click chemistry has found new uses in biomedicine. Professor Sharpless, please.
Thank you very much for kind words. I'm very glad to be here. I owe that to Earl Anderson, Bengt Norden especially, who's been my friend since quite a while back. And he likes trips to nice places, and he also is a sailor. But he doesn't take much time as he should doing that, I think. Because you can think out there, you know. And I like to be alone when I'm thinking. I can only think then. I'm distracted very easily. So I hope I can get through this presentation. It's going to be a little problem because I gave up on PowerPoint, which I had everything on. I went to Keynote. It's just about killed me. Where's my glasses? Okay. Anyway, I'm going to give up forever on PowerPoint. They've had it with me because this is just unbelievable. Especially maybe it's a Lion upgrade. I don't know what it is, but it's no fun. And and we're getting viruses now too. I think this world is melding too close in the computer business. We ought to stay with a strict border in between. No, we have to get rid of the border, obviously. That's what's the problem. Okay, yesterday, with Greg Venter here, especially beautiful high-end work and what could be done with our input into DNA technology, our very large input, but very little input, really, because we're such blunt objects, really. Everything has to be done to remove, and we can't see the things that we work with. And when you think about it, everything we do is intentional with vision, usually, or sound, or touch, but, chemistry is just use your hands, use muscles. There's nothing else going on except the brain is instructing the muscles. And so that's Avogadro's number in 20 times there, 30 times. And it's probably, as a solvent, I throw in a catalyst. I think, I'm in control of this? I don't think so. It's statistical mechanics. We just have to realize that the world exists at our scale, temporal and spatially removed from the other scale. We're about 10 to the 9th times slower than enzymes doing their job. And when they do their job in those little 10 to the minus 9th bits, if they could see us and they watch us blink, the blink takes about a third of a second or so. If they could see that, it would take over a year, I roughly calculate, for us to blink. So now I'm going to show you a movie that shows a slowed down version of a cartoon of DNA replication. You can get it yourself off the web, and there's some lousy copies out there, but if you go right to the Walter and Eliza Institute, you'll get, you'll get the best version of it. It's really much better than the ones I had before. And many people, even Shekhanover and Herskowitz, didn't know about this. I saw 2 years ago in China, and they came running up. They wanted it, of course, because it's their world. But I think most of you have seen it by now. So what I want to do is start it off, and I'll try to go through to the, I'll go through to
In this animation, we'll see the remarkable way our DNA is tightly packed up so that 6 feet of this long molecule fits into the microscopic nucleus of every cell. The process starts when DNA is wrapped around special protein molecules called histones. The combined loop of DNA and protein is called a nucleosome. Next, the nucleosomes are packaged into a thread. The end result is a fiber known as chromatin.
I know it's interesting. I'm going to skip this part now.
This fiber is then looped and coiled
It goes
yet again.
through another part here. That's part which is real, false. It's a electron microscopy of a metaphase of a dividing cell. That's the only real thing in the video. See, there they go. Now here's the part which I think is very disturbing for a chemist to see. And it's slowed down, as she'll say many times, so that we can see it. We only parse about 22 frames a second. Essentially, the world is a moving picture for us. And then you'll see things are really complicated for the other strand. This is polymerase, and it's helicase. It's making another copy of DNA, double-stranded DNA, in order for cells to divide. And I'm going to come back to this because if you fool it and put some DNA in there, you can do click chemistry on some nucleic acids, then you can label it. So, but watch what happens when you...
Using computer animation based on molecular research, we are now able to see how DNA is actually copied in living cells. You are looking at an assembly line of amazing miniature biochemical machines that are pulling apart the DNA double helix and cranking out a copy of each strand. The DNA to be copied enters the production line from bottom left. The whirling blue molecular machine is called helicase. It spins the DNA as fast as a jet engine as it unwinds the double helix into 2 strands. One strand is copied continuously and can be seen spooling off to the right. Things are not so simple for the other strand because it must be copied backwards. It is drawn out repeatedly in loops and copied one section at a time. The end result is 2 new DNA molecules.
Yeah, things are not so simple for this second strand. I shouldn't Englishman, that's all he would say, but I will say that it looks like a train crashing into an airplane to me. I don't know, it's just unbelievable, it shouldn't work. It's so fast when you think about all the false bounces that have to go on at the entry zone where they're putting in the nucleotide phosphates to make the bonds. It really gives you a pause. You can see why a blink is a lifetime down there. And not only that, it's down in the level where quantum effects can occur, and we are up here, and we're designed to work at keeping alive and jumping over rocks and making brave jumps to get away from a tiger, and all these things that we do have little to do with participating down there, the machine that runs us. Okay. So let me go to... I think, oh yeah, I want to show must be on the other slide. Yeah. This is just from the web.
You able to find your keynote?
What? Is something wrong? No, I'm okay. I don't need the sound for this, but... Okay, what is this thing? Well, this is a home experiment. It's on a warm surface. This is it could be frozen honey, or it could be beeswax, or it could be just silicon oil with a little metal in it so you can see the convection cells. If you start warming, it's only about 1.5 degrees where this instability breaks out. And these are probably, in that high plate, they're probably about a centimeter or two across, I guess. And you can see they're not totally perfect, but if this thing was with no edges and had a bit of a more homogeneous makeup, it's pretty bent, it would form beautiful hexagons across the surface. And in the middle of the hexagon comes up the fluid. It goes across and comes down the outside, and they're pretty isolated. You put dyes in, they take a long, funny time to go across, and they go across in a very weird way. So these are called, by some people, physics-own organisms, because they start, before they reach that first dissipator stage, they're going along, just a little bit of energy is being leaked through the system by conduction, Coué flow, and laminar flow, and just conduction. But then you reach a certain point where a phase change occurs, and it's just amazingly jumps. And it goes, what's really interesting about this, Brownian motion and things that are happening at the prior moment are, here it comes, you can see it when it starts going abruptly. They didn't show the smooth they should have. That's what's on the surface of the sun. They're about half the size of the Earth. It's covered with these Bénard cells, so you can see them. The clouds often have, it's the ideal close pack on a plane, and of course the bees have it in spades, and they also have a rhombohedral dodecahedron, which is the best close pack structure when they're capped of anything we know in math or 4 dimensions. And I shouldn't spend too much time on this, but what this is these have a structure that's very up there. It's part of life structure. It's what causes the cilia beat currents. And if they're ablated, usually the fetus dies. But at the beginning of embryogenesis, the current is part of the information. And if it's not there, the heart ends 50-50 chance of being right or left. A lot of other things go wrong because ontology is so locked into subtle things, and it's the most interesting part of multicellular life, how it gets to where it's going. Anyway, you start at 10 to the minus ninth atom size, nanometer. You end up at centimeter size things. You can see them now. So that's a metaphor for what we have to achieve between chemistry and life. And life is one of these systems very much like this because it's a dissipator. We're a dissipator. We take, especially us, big animals, we take in a lot of heat from food. We pass the heat through, and we're only alive while we're passing that energy through us. Could be any other thing down here. It wouldn't have to be DNA. It could be some other replicator. But the main point is that we have, we're dissipating energy. The whole planet is doing this, and we're actually participating in a free energy capture that makes the Earth happy. It gets it stronger. It's in charge of everything, really, life. So as a group, we're symbiotic, and everything right down to the cyanobacteria and up to the blue whales. Okay, now, and it happens emergently. There are many forms of these subtle forms of the dissipators that emerge at the same level of energy dissipation, all different structures. And they go from there on to be different. They have a memory, just like they're not reversible in time is what I'm trying to say. You get down to the level of tiniest things in the universe in physics, they're all time reversible more or less in principle. But once you get up to a dissipator system where your entropy is dropping fast, you don't have that. Okay, that's something. When I see it, I fell in love with this Bénard cells. It's not me who interprets them. Rod Swenson does. I actually wanted to talk more after I heard yesterday's discussions about what it takes to find things, how to find something useful. And I guess the thing I'd like to just pass on, I have a lecture I've been working on over the years. I'll gladly give it to you. You can put it up on your university website. It's how to find something useful. And it's really about the most important thing of all is living with uncertainty. You have to like risk, and you have to not be doing anything you know you can do. That's a waste of time. I mean, there's too many things. It's an infinite regress to the end of the universe to study peanut butter, for example. I mean, it doesn't really, it's just the way the world is at our scale. So I would say, try to work on something you don't understand, and then keep your eyes out like crazy for anomalies, but try to learn to tolerate risk. And you'll be happy because it'll keep you busy. Okay. I'll pass that on to you as a movie. Now, this is an interesting, I think I'm going to have to stick to these, because for a while, I'll just stick to the things I know and can trust. Okay, this is a fancy piece of equipment, obviously. It's made in Germany, in Hamburg and Freiburg. I think there's a collaboration. And it's a laser that's focusing on an embryo. Now we're going from the side, of molecules in DNA, which I'll show you back in a minute. We'll show DNA replicating and being followed by labels. But this is DNA, this is not DNA, this is the whole shebang. This is actually in about 10,000 cells are formed in 26 hours, I think, from the moment of fertilization of the zebrafish egg. It's a big yolk with a tiny little thing on top, and it takes 100 minutes for it to get its 34 cells marched out to as far as they can, and then all hell breaks loose. And you're going to see the all hell breaks loose part here. But how do they do this? They track all those cells with a huge computer and a laser that's really gently fluxing through in every dimension and not killing the things. Because yesterday, that question from Korea, Heisenberg's principle, it's not that so. There's so many things you can do with energy. Once you hit a system with enough energy, it can't take that. Life has to be within 100 degrees. It's a very small range, but thank God for water. If we ever lose our water, we'll have gone long before it's gone. Okay. So, is this going to go? Even this doesn't want to go. Oh well. Yeah, it just goes. The sample's over here, and it goes up and down, and it's looking at everything. But it has to go fast enough to keep up, because they're moving the cells. It has to keep. It loses none of them. Maybe a tenth of a percent of the count is untracked after a certain point. Let's hope the next one works. Oh God, this thing's stuck. Okay, that's the problem. Okay. Now we may have to go through some rigmaroles. Now, I want to find the zebrafish. I think I've got it on one of these lectures now, and I'll just have to find it. Okay. Well, I can just open it here. This is number 8, I believe. There's 1 gigabyte. I got this in China a year ago from a man who's grateful I gave him my library of papers. And so he gives me this, but he came off the web from the publication, the German publication. Is it open? Yeah. Oh, here. Okay, if it works, you're gonna see some fast gymnastics here. It's going to start. This is the start point, and you have to imagine some giant yolks here. The yolk's probably this big. And this is looking down on the yolk from the top where the fertilization took place, and they've scattered. They've already started to morph into different things, but they're run out to their goal posts, and they're ready. And over here you can see them from the side. Now remember, this is going to be a picture that's pulling back in time because it's going to encompass the whole yolk in about 300 more minutes. It's starting at 100 minutes. Let's see if it stops again. And so they're pulling back constantly. It's growing as a cap over here from the side view. And this is, and what's happening here, the cells this counts cells, this counts nuclei, this counts motion. You see it goes through cycles and slows down. This counts chromatin. So they start out more or less in sync, and they keep cutting and replicating at the same approximate pace. And now over here, you see what happened? It went up to 8,000, about 6 or 8,000, and then it starts down. That really caught my eye. Because, you make your body gets made as a fish a little bit, and then the webbing has to be taken out. They do their embryogenesis in one day. Now you can see the backbone coming in here. This is the head, the eyes. It's stretched. This is a stretched 747 here. But the reason the screen is stretched too much, but I don't know if maybe I can change that. Let's see. I don't like that stretch. Oh, I don't see it. Oh, yeah. Oh, did I screw it up? Yeah. Okay, something. Okay, now you see that you can have this movies. I can give the whole set to you. I just thought it was rather the most remarkable thing I'd ever seen. And I just thought it was like, okay, now we have all this maze of stuff going on in the cells. They're all differentiating. They're all getting instructions about who their neighbors are going to be or who they will accept as neighbors, and that's all ion channel business. And also the cilia are beating around and doing various things. So they all become part of the whole. I'm not going to do it. Oh, sorry. Yeah. Okay, I'm stuck here. Now, this is another thing about the speed of things as far as man can keep track of what's happening in a body like ours. I think that's where we make mistakes. We're just picture-oriented, static creatures. We're always looking at things sitting still. That's all we can really do. And then we have to extrapolate from there. Unfortunately, many people don't worry about extrapolating. It's easy to make mistakes. If all you have is visual, then you can't trust it. Our brain really warps our vision for its own benefit of survival. This is a PET scan by one of the, we did this with a carbonic anhydrase inhibitor made by click chemistry. And show you the, maybe I will and maybe I won't. I think I have to go. Yeah. This is a half an hour time span, so you're seeing a slow motion. And what you're seeing here, it'll loop, it is a mouse that's been injected with a attomole or even less of F19 positron emitter. And so this is PET scan, and it's on the carbonic anhydrase inhibitor, which we optimized by click in situ, and it goes up to the kidneys, goes through the heart, lungs to the kidneys, and also it's going again now. And you notice this coming into view is the spleen. The spleen has carbonic anhydrase too. I mean, the blood does, but you can't see it until it's collected in one place. So the spleen would have been visible. It doesn't have any more blood in it, but you understand the label's coming in. Okay, this mouse had an inhibitor made the same way. It was a higher binder to the COX-2 inhibitor, which is a good, these are cancer targets. Outside of cells have these kinds of recognition things on them, and if you can bind them, you can make a tumor probe with PET. Watch what happens now. This mouse was injected in the tail, it went up through the heart, lung, and I think it was in less than a minute it appeared in the common bile duct, and not a bit of it went through into the mouse. The first pass in the liver. This was found out in 2 months by Hartmuth. He had a good-looking drug. It was binding through to the cells, killing COX-2, but the little paws up here, the little tiny paws, they then show they use a large cold dose to show that this compound doesn't leave any, doesn't ablate pain in the paw edema test. So it's gone. So it looks, this you can tell real fast if you have kind of visual, these things that we can understand, visual tests. Okay, now this is, we had an idea, MG and I had an idea, MG Finn, we both had it one day after reading Kevin Kelly's book, and we all say he changed our lives because it was the day we realized that we should let the enzyme make the last step in an inhibitor synthesis. It makes the Cinderella fit, as it turns out. And I think the med-chems make mistakes here. It's like being the ugly stepsisters trying to shoehorn things into a very delicate target, the enzyme. It doesn't really doesn't surprise me in hindsight that it doesn't work well. I just want to show the amigos. We consider ourselves clicking amigos. Hartmuth has gone to Siemens, but Valeri, MG, and I are now the three amigos. And these guys, I think I better pull out. Okay, I'll stop here for a second. This is a C hair. This is an enzyme from a C hair. This is a more mammalian version. The aplesia, the little C hairs that you can barely see, they're very delicate. They swim off of Aloya, even where I live. At low tide, you can see them. It's the top part has been cut away, but it's floating around in the blood, not on the lumen of the nerves, up as it is. It's the nicotinic receptor. It's all kinds of receptors. These are the receptors that make you feel good, bad, and this is nicotinic is, of course, the one that makes us love smoking. So we take that thing off at the top, and this is moving slowly, but it's really it's 5 subunits. They're all identical in this case, and those things opening. This is X-ray structures. It was Palmer Taylor's jewel in his crown, because when it's all the way open, it has cobra venom toxin. And so it looks exactly like a starfish. It's huge arms coming out. And then when the smaller things are in there, like strict alkaloids, you get different positions. And so the agonist position is when it has a little tiny cat ion in there and closes on it. That's open channel. And when you put you more or less inhibit it variously as it goes out. This is very slow motion picture of that site. It has a conatine. I think I forget which alkaloid it is. It's a good binder. And you see, it closes, opens, closes. But it happy in the closed form. It's an agonist. Antagonist. No, it's agonist. Okay, here comes another one. This one is amazing with these fellows at UCSD. Palmer, we work with him. We couldn't possibly get pictures like this ourselves. Here you have the protein that you saw from the top in a stick figure, and it'll have a water surface on it shortly. And this is the disulfide bridge in the flap. And it starts, it's a bit slow, but you'll see now, put the water surface. Now into that flap is going to come a nicotinic type compound. It's going to be a tropane thing we put an azide on. See, there's the azide, and it closes on it because it's got a quad salt. And now we fished for things in situ, and we got about 20 different things. And they went down to picomolar inhibitors. So it was an easy way to find a good inhibitor. So accidentally the other day found it goes backwards and forwards, so I like it this way. It's going back. So the idea is that it works. You can use molecular scale reaction vessels to go fishing for things that might not be found otherwise. And that's what's interesting about this story. Well, Kevin Kelly's book, and he's out of control simply means you aren't anything if you're not out of control. If anything we're going to plan to do, you can bet it's not going to be very interesting or work, because life is embedded so far back, and she doesn't know what she's doing. That's why it works. And she only has to answer the live and die question. And so if you don't export control, you can't be a god. In SimEarth, Kelly was familiar with those SimEarth, SimCity. You have to give the system. You have to realize you're working now with a system. The internet is the same mysterious kind of system. It grew itself, and only by growing yourself can you be subtle and embedded and unpredictable. So we went fishing for things. We had about 98 chances, and these are the two that hit. And they were stunningly successful. We couldn't figure out what happened for about a year. And finally, we enlisted Palmer because we found out we should have done that early. Here's the two binders. They're both good binders, micromolar and low micromolar and low nanomolar. So if you multiply those together, you should get a good inhibitor if it's well connected. And this one came out really good, 77 femtomolar. It has an off-life of about 2.5 weeks. It's very hard to get the kinetics. It's the fusion control on rate, and its off rate is all that matters. It was the most potent inhibitor known. In fact, after that, we made attomolar from this type system, and it became attomolar, and that's 27 kcals, and so it just might as well be a bond. The thing that's really interesting about this system, though, is this. Here, I'll show you. There's the gorge. The gorge is 21 angstroms deep. Remember, this is the fastest enzyme, esterase, or in all organisms that have a central nervous system. It's convergent from different original forms, but they all have this big hole. And in the hole, in the wall at the top, are these amino acids with aromatic quadrupoles. And the tryptophan especially, if you take it out of this enzyme is dead. It doesn't work anymore. So it's clear that that guy is doing something to grab the quad. But we found out by doing this in situ, we found out what it was doing, according to the experts. They think, see, here it's stopped now, and I'll run it backwards by my hand. Right there is a big tryptophan at the gorge mouth. This is an ethidium, which gives it Palmer had found that binding site. You can block the hole by just having an ethidium, and it blocks the entrance. But it's not down at the bottom. The bottom is where the drugs for Alzheimer's go and block the rate of hydrolysis of the transmitter. There's the active site where sarin and all the nerve gas things act. And this is the creature with its syn triazole. It formed a syn. Next day, Larry told somebody, talked to me, we said, well, we got to have a way to make syn and anti, it appears. And so the next day we discovered that QAC reaction. It's that simple. We decided, we got to have it, and we put copper in. Now, the fact that copper in acetylene azide had never been encountered before. It was just hard to believe. In fact, I think it's still out there somewhere in the old German literature. If I go backwards on this, I'll just show you, you see that, watch at the top of the slide. Is that tryptophan coming in and out? It's about 3 or 4 kilocalories up the energy surface, according to McCammon, who's an excellent computational chemist that works with Palmer at UCSD. So what happened here, because I'm showing you the crystal structure, when it's down at the bottom, that's the final point, that's the crystal structure. So the enzyme has been trapped up there. We call it a freeze frame inhibitor. And it's just clunk, and that was where the catalysis to make an azide was. Of course, it didn't know it had that skill. Like everything that life finds, it doesn't really register in any writing or anything. So this was our encouragement and started us off really thinking we could do this kind of thing, but it's not really a very practical method except for LC-MS. You can do it automated in microchips. But you get a teeny little bit of product, but that's all you need. That's the clue about the Cinderella fit. And there's the gorge ripped open on the right, and the one on the left is not the syn, but it's the anti. It's still 300 femtomolar, so it binds damn well, but it doesn't open it doesn't pull the wall apart. See here, take it out. This hole on the right, on the left, every X-ray, and there are about 60, empty, full with various things, they always showed those two in the wall before. So it makes sense that this might be part of that 10,000 per second Vmax. So the conclusion from that was that we were lucky. Strict chemistry wasn't going to be just modular with a few good reactions. You know, the idea of a few good reactions that get function. It's the Marines, a few good guys, men and women, you can win. Okay. Now go to where? I think I messed things up. Maybe I have to go back on the screen. Okay. When I have how phobia-based discovery or fear-based discovery have a reading list of things that I think are really good for scientists to read. And Harry Croto was right. I mean, I didn't start doing it myself really until I got the scripts as much as I should, but I read, pretty soon I was reading 30% of my time outside of my own field. Catalysis and synthesis, and that and other things too, but it's technical things. You should never stay, even in graduate. By the time you're in graduate school, you should spend about 20% of your time reading other fields, because the progress in the world is going to really take us to the point where the disciplines are gone finally, and because they're really not useful anymore. Each person needs to know a few things, and one of the worst things I see in my experience is that the biochemists, the smartest ones especially, they have beautiful papers. I read them because they're wonderful to read, the logic and what they did and what they know and what they don't know. It comes out clearly. But there's not a molecule in there, the kind we make, the small ones, the cheap ones. That is like an ablation between the two fields that is painful, because if I can see molecules, I can tell some, I got a lot of things like that, made them 10 years ago. I'll just take them and see what happens. And no, we can't do that, right? Next door, there could be this person. But if they don't take 6 months and learn how structures are put together and make that a requirement, you'll change the world. Because most of us want this biological function. We talk about other functions, but let's face it, especially the older people who have the money want the biological functions. But I don't think there are other functions too that are marvelous that chemistry can do. We all know that from plastics and polymers. Now, I have some quotes from Emily Dickinson, which I won't bother you with, but I just wanted to I guess I will, yeah. Emily Dickinson, my wife found her while we were writing these things about how you discover something new. And the fact is that all the great inventors say failure is the most important thing. If you aren't having failures pretty routinely, maybe 95% of the time, you're in a pretty dull area. You don't have any walls to, you're not feeling the next mountain around you. You're just down on the plain. And so anyway, Emily Dickinson she was very shy, very creative, and very brave in her mind. And she was like I think along with not Emerson, but Walt Whitman, she was the greatest 18th century poet in the end. She wasn't published during her lifetime, but and she just, her poems are loaded with this right in your face, Mother Nature, please show us. Dickinson faces down the primal unknown in a fearless and uncanny way, as if saying, yes, we know you harbor big surprises, and we'd be thrilled to see them. And this is one of the, knowing not when the dawn will come, I open every door. Jesus, I mean, and here's the one that's my favorite, because it's about energy dissipation, which is really what life is. You could look at it, but with this much of an energy gradient that's sustained, you know there's a life form, I think, on the planet if you look from far away. The pedigree of honey does not concern the bee. A clover, any time to him, is aristocracy. I took one draught of life. I'll tell you what I paid. Precisely an existence. The market price, they said. Yeah. You like that one? Oops. What did I do? No, I'm okay. Sort of. No sleep on account of PowerPoint. Nah. There's the team in front of a blackboard. M.G. Finn. M.G. Finn started the bioconjugation. You should never forget that. People like Cravat and Schultz and others were almost publishing it before, because M.G. is a wonderful mensch. He taught them, all the students, to publish it. And he and I take a long time to publish anything, me especially. Could be 3 years, unfortunately. And so, anyway, Finn was the first to do the thing that leads to what's coming up, the labeling of DNA. So I have to hurry along and show you that. This was Falken's discovery that this reaction is unkillable. There are only about 6,000 triazoles in 2000, say one even. And then suddenly, if you go and have abs, there's now, of this type, there's now there's now probably almost 100,000, just because they're easy to make. And it was simultaneously discovered in Denmark on a solid phase by Meldal, but they said it should be anhydrous and it had to be on a solid phase. So Falken is the one, we knew it was a click reaction because all click reactions love water, the interface especially. They really want the interface, and that's important. That's sort of like life itself. It's like chemistry occurs between oil and water, probably the most in enzymes often. And there's the trick that these two men, his student, Salek, Adrian, and Mitchison, they just cast this off. They did some more, but they just put it out as a method for watching DNA. This was the emergent thing I wanted to show you. And it came along that they would be able to label by feeding this little uridine, this little acetylenic analog, and it went in fine, and it didn't hurt the creatures. They could live for months, and that carry that around and show what they were doing. And here is the, I hope it works. These are HeLa cells on a confocal microscope. And from the woman who died, Henrietta Lacks, in 1951, she died. So these are old by now. And I wonder what they really are, because they're kind of worrisome about what they mean. I mean, they've been around for a long time, and they're still going. All right, this is the big, every day they replicate. So one day, an hour pulse of EDU was given. And so millions of these analogs went into the new cells. And the new cells knew everything, right? New insides and new proteins. Oops. Oh, yeah. So there it is, cycling. That's about, it goes over in 2 seconds, but it's about 9 minutes, and you can see nuclei really bright. In fact, there's only about 0.5% labeled, because these cells are almost as they were. They were fixed just before, have a few holes in them, so that the copper, which is flowing through the stage of them now, and the dye, which only lights up when it clicks, it's quenched otherwise. So there's no background noise, and this people love. Now, why it works because this reaction is alien, and it doesn't care about anything that we care about, or even by life standards, it's kind of an alien reaction that will be hard to stop. It's the last reaction standing. Anyway, Salic then went forward and used it himself on a lot of cool things. I don't think all of this is published. He labeled DNA, and here it is at the metaphase where the cells are dividing, and this is labeled, this here means DAPI. DAPI is all the DNA is labeled. Over here, this was pulsed for 1 hour in its S phase with EDU. So you see it's only spotted, it's only labeled in patches where the part was being made while it went through. Then it's chased. The pulse chase is what they call this. And then if you look at the villi are sloughed every 2 or 3 days. That's why we get really sick. We die from loss of our insides at the intestines. The intestines have to be rebuilt constantly. They're the interface getting the food, and they get beat up. And so here comes the bottom is labeled on the first day, and you see it down and then it starts coming up, and then it sloughs off. These are the cells that got labeled by the pulse. And this is a mouse, the same mouse. He did a lot of nice experiments with one mouse. He just fed it, labeled everything that could be labeled, that was making cells. That's what you can find this way. You find wherever a new cell has been made. Small intestine labeled with EDU, the pink one, which lights up pink in the screen here. You can see that that the villi, and the blue is the rest of the DNA. So that's DAPI stain. This is the bad news for us who like to learn. I hope we can keep going. This is the brain of that mouse. There's not one new neuron made, and that's the nucleus of the neuron, because you see that's all. This is either a glial cell, which does divide, or else it's maybe just an artifact in the cut. He pieced together thousands of his confocal things and made the picture of this 1.5 2 centimeter long section of the intestine. And then he's got 3 T3 cells there, and he's labeled them with propargylcholine. Now, he's also got RNA labels. I don't know if I show them here, but the red color is the dye of propargylcholine. And actually, it's not that simple. Let me go to the next slide. What he's got here is that the green ones are biotin azide, which has streptavidin along for the ride, so it's big. It can only reach things on the outside, the membranes on the outside, the phosphatidylcholine, and it gives the green on the outside. And now inside, you can get the little guys in, but also it's labeled on the inside. It's stained blue. You can change the color of the dye by the tricks used in the structure. There's the group it scripts as of about a year ago, and it's changed. It's different now, but I don't have my new hero, Jia Dong from Shanghai here, and I don't know how that got in there. Anyway, this is okay. This is now going to be that other labeling experiment. Now I show the phosphatidylcholine, and I'm sorry these got out of order, but it really lights up with phosphatidylcholine. So it seems like you want to see things in a cell, even without labeling, of course, because it doesn't have to replicate to do this. Lipids, sneak in and out all the time. And this is the part I loved about Valeri. All these things didn't matter to this reaction, so you didn't even need copper soluble. It made its own catalyst. These are ligands for the copper that really are perfect. So just the wire is enough, and you start at room temperature. But then he went over and got 10 cc's of his own blood, a nurse he knew in the hospital right next door. He centrifuged it, and it works better in plasma. That's what you call strong inference. I'll give you that article if you want. You should read that. You should never enter a lab without strong inference. That's the way sometimes you feel, and other days you don't feel like that. This guy reminds me of Jing Kwan, my colleague. He's so excited all the time. And okay, now why do they take all that time to show you this for sale kit from this company? Well, it's one of those things that happens that suddenly emerges. You know, it's not anything I did, and maybe Murchison and Salick, I may not have even known exactly what it was going to do. But when you can watch DNA replicate, that means you see the turnover to another day, and a life has made a closure on a new organism. It's duplicated itself. That's the whole ball of wax right there. So so what they're using it for. I collected a lot of papers, maybe a couple thousand, but I've got about 1,000 of them in this database. You're welcome to have them. Here, someone's studying the Arabidopsis and Arabidopsis root, and you can see just at the tip where the EDA is being incorporated. And I'll show you one more from this. And this was a one-page publication called "Visions: The Art of Science," and it's one by Seibert and German, who's moved back, I think, to Germany, but he was Brown, his Italian postdoc. This is a Cynarian. We're all directly related to Cynarians. Whether you like, it looks weird, but they had everything. They even had the box genes. They were getting ready. They had muscles, nerves, box genes. They were going to do something. So they had to decide, and they decided sometime down the road there. Not cancer. This is a normal cell. It's been 5 days. It's a normal part of a big chain of jellyfish, and it's making cells where it needs them. It's not a cancer situation. So, okay. Now, finally, I want to show you I collected hundreds of them, but I'm not going to have. We just got way behind, obviously. So I just want to show you the papers program. I think I'm going to kind of get back to the. Okay, let me see if this works. So this is the papers program for Mac. I think they got it for PC too. And I couldn't live without it because I'll show you why. You just dump PDFs into it, which if you have rights to get them from the journal, you could do at home through the VPN. And okay, now it shows you, let's put it by title. And you know, it has searching, really fast spotlight searching. It searches every word in every paper, and it has all the metadata. And so if I search all, I search every word. If I search these, I get restrictions. Let's see what we got here for Singapore, for example. There must be something from Singapore in here. And this is the way I find out who I want to talk to when I go to a place. Singapore. Like in Vanderbilt. Before I came here, I was at Vanderbilt. They got a lot going on there. So let's see now. How much do I have to get it smaller? Yeah. So I have about 10,000 papers that are click papers, but I gave up on that. It was hopeless. So I just go to the one thing I like is this emergent thing, and I also, now we got the other projects. Don't look at the other titles in here. It's a secret I can't talk about yet, but no, it doesn't have any results. It's just the history of the chemistry. Now if I go up here and put, what else should I put? China? China is going to be big, I think. They got to publish a lot to survive, the young people. Oh, it can't be that big. No. What's wrong? So, okay, something's wrong. Let's try. Yeah, you know what's really impressive is the Netherlands. I don't know if they call themselves the Netherlands or Holland. For a small country, they got a big operation in practical chemistry where they need to know what's happening at the molecular level. But now I'm going to go and look for click. Now this is the way the trademark is written. And I'm not advertising this. I just think it's easy and I can show you how it works. And I need TM, so I go to one of these little things where I have my favorites. And there it is. That gets in there. Now if I search for that, it should give me the Invitrogen things, and you'll see there's about, there's almost half of them are these kits. And it's mostly an EDU, but it's also for RNA, and they've got them for sugars and everything. And let's go look at the flags, because the flags I put in, I'm just going to search for the ones that I flagged, because they're my favorite. And if you look at, or some of my favorites, if I look at this, I'm really only interested in evolution ever since I was this big. And so you can see which ones I've got up front here. They're all embryo. They're all about that process that's really complicated. And if you look at, I'm almost done. Yeah, I just want to show them one of these. Where is it? C. elegans germ? No. Okay. One. There's one here that earmuff. Oh, I think if you'll see that by looking at how you can see a whole backbone in the embryo, because if you put the DNA in at the front of the notochord time, it goes all the way down to the end, and it gets fainter, which is a sign of temporal elongation. The DNA is getting split every time it divides, but it's still there with the acetylene. So it's a time, you can have a real time window to watch ontogenesis. And it's stem cells. Half of those references that show click it are for stem cells. They want to know where they go, and they can tell because they light up when you take the organ and look at it. Okay, thank you for your patience.